Thanks, Robert. Is there a... Oh, okay. Yeah, so thanks for the introduction, Robert. This talk is about quantum state tomography. So here's the basic problem. You're given copies of an unknown state, rho, and it's a d-dimensional state. And you just want to measure these copies in such a way that you can make an estimate. Just wondering if there's a pointer. You can make an estimate sigma that's close to the unknown rho. Okay, and you want to use few copies as a function of the dimension and this notion of close. But that raises the question. Click. What does it? Oh goodness. Yeah, what does it mean for two states to be epsilon close? What does that mean? So there's several possibilities. So here are 4 notions of what it could mean for states to be close, or 4 notions of the distance between two states. So the first 2 are probably the most common. The first one is the trace distance, which is basically the L1 distance between rho and sigma. And the second one, I mean, it's a funny notation, but it's basically the infidelity, like 1 minus the fidelity between rho and sigma. And this is sometimes called the square of the Burris distance. But that's not the only 2 measures you could have for closeness. There's also the relative entropy, S rho sigma. And there's this 4th one, which is about the one I'm going to talk mostly about in this talk, which is the chi-squared divergence, or more specifically the Burris chi-squared divergence. Because in fact, there's lots of different kinds of chi-squared divergences for quantum states. Now, one way to keep track of all these quantities is to know that they're ordered here in increasing size, at least if you square the trace distance. So you might notice I stuck a square on the trace distance there. And when you do that, you get this chain of inequalities that trace distance squared is smaller than infidelity, and that's smaller than relative entropy. And in turn, that's smaller than chi-squared divergence. So the trace squared is the smallest, and the chi-squared is the largest. And that means you get different notions of strictness or closeness as like a quality guarantee when you have a tomography algorithm. So if you manage to find an estimate sigma that has small squared trace distance from rho, then you could say that, oh, I found a close estimate of rho. And if you did better and found one that had small infidelity, then you might say, oh, I found a super close estimate of rho. And if the relative entropy was small, then I'll call that super duper close. And if the chi-square divergence even is small, then I will say that these 2 states are ridiculously close. Just a few quick comments about this. The first 2 are always numbers between 0 and 1. In fact, these are distances, they're metrics. But so relative entropy and chi-square divergence are not even bounded, so they can even be infinity in some cases. Okay, so what's known about full state tomography? There's this result from 2016 that says you can do state tomography with order d squared over epsilon many copies, and this will give you closeness of your estimate. So the trace distance squared will be at most epsilon. And a similar result was proven around the same time that achieves super closeness, or infidelity, which is smaller than epsilon, with about the same number of copies. This O twiddled means ignoring some logarithmic factors in d and epsilon, which I will do in this talk. So this is mostly a strictly better result. And the work I want to tell you about today with Steve is that you can achieve even ridiculous closeness of your estimate using the same number of copies, essentially. Okay, so before we get into that, you might ask this question: why do you care about this lesser known notion of the distance between 2 quantum states? It's chi-squared divergence. So let me tell you a little bit about the motivation for that. The main motivation for me comes from this area or problem known as hypothesis testing. So this is a problem that's similar to tomography. It's the situation where the state that you're trying to learn something about is not completely unknown to you. At least you have a hypothesis for what it's supposed to be. So you have in front of you like a fixed state sigma written on a piece of paper that you think or you hope that rho is, and you're just trying to accept or reject the hypothesis that rho is equal to this sigma. So if rho is really far from sigma, you don't care what far state from sigma it is. You just want to know that it's far from sigma. Okay, so for this problem, chi-squared divergence plays a really central role. And this sequence of papers which studied the hypothesis testing problem, both in the classical case of hypothesis testing for probability distributions and the generalized case for quantum states, they kind of showed in a sense that the correct way to solve this problem is to try to empirically estimate the chi-squared divergence of the unknown state from your fixed hypothesis state rho. And because of this, it somewhat motivates this tomography problem of trying to learn an unknown state to closeness in chi-square divergence. And in particular, an illustration of this theorem I had with Bodescu and Wright, showed that with just d over epsilon copies, so that's better than the d squared over epsilon that you need for tomography, you can kind of tell the difference between these two cases when the unknown state rho is ridiculously close to sigma, or whether it's the case when it's not even super close to sigma. Okay, so this is one motivation for studying chi-square divergence. And we use this connection together with our result about improved tomography for this chi-square divergence to get a new quantum testing algorithm for the property of having zero mutual information. So let me tell you what this means. In this task, there's again like an unknown quantum state rho, and it's a bipartite state. Okay, so it has an A register and a B register, both of dimension d. So rho is of dimension d squared. And we show that with this many copies of the state, d to the 2.5 over epsilon, you can tell the difference between the cases where rho is a product state, it's of the form rho A tensor rho B, and the case when it's sort of far from being a product state, in the sense that there's like a decent amount of mutual information between the rho A part and the rho B part. So in particular, at least epsilon mutual information. And so it's kind of like a test for being a product state. And what's maybe important about this is not so much the dependence on d, but the dependence on epsilon. So I can tell you that even for the case when d equals 2, and you just have two qubit states, and you're interested in the mutual information between the first qubit and the second qubit in this unknown state rho, if you want to actually estimate this mutual information up to an accuracy of plus or minus epsilon, this needs a number of copies that scales quadratically in 1 over epsilon. But our result shows that if you're just trying to tell the difference between, product state, which is zero mutual information, and at least epsilon mutual information, then you can achieve linear scaling in terms of 1 over epsilon. So this part of our paper is a consequence of the chi-squared tomography algorithm, which I'll tell you about. And I just want to add another little anecdote here. So you can consider the same problem, the classical version of it, with probability distributions. Like you have a probability distribution over a product set A, B, and you want to tell the difference between the case where the two marginals are independent or they have at least epsilon mutual information. And this problem was recently studied in the classical case, and they got a similar result, but if you just take our results and take our proof and specialize it to the classical case, you improve on the best known classical algorithm. So it's not a quantum algorithm for a classical problem, it's an improved classical algorithm for a classical problem that was inspired by our quantum methods. Okay, so that's a little bit about the motivation for chi-squared tomography. And now I'll tell you a little bit about this main result. And the first thing we have to talk about is what is this chi-squared divergence? So I haven't even defined it for you yet, and it's not super well known. So let me take this opportunity to tell you about it. So it's a generalization of the chi-squared divergence between two probability distributions. And like every proper and good notion of the distance between two states, it has a property that is unitarily invariant. And what that means is if you have two states, rho and sigma, and you look at the chi-squared distance between them, it doesn't change if you change bases. So if you conjugate them both by the same unitary, it doesn't change what the distance is. And that's a very natural notion for a distance to have. And because of this, it means I can define for you what is the chi-squared divergence in the special case that rho is a diagonal matrix. Because in the general case, you can just change bases to make rho diagonal and figure out the chi-squared divergence in that case. And this makes the formulas a lot simpler to understand. In fact, I can even insist on this extra condition that the eigenvalues, the diagonal entries of sigma, q1 through qd, are in decreasing order. So I'll just tell you the definition of the chi-squared divergence between rho and sigma in the case when sigma is diagonal of this form. Okay, so here's a picture. We have rho on the left, and we have sigma on the right. And before I say the definition of chi-squared divergence, let me remind you of a fifth notion of distance between quantum states, rho and sigma, which has one virtue and one benefit. The virtue is that it has a very simple formula, and one virtue and one problem. The problem is that it doesn't have a real great interpretation or meaning. So there's natural meanings to trace distance and infidelity and relative entropy. I'm talking here about the Frobenius distance, or just the L2 squared distance. So this measure of distance between two states, rho and sigma, is just like the L2 squared difference. You really just like take all the entry-wise differences of the two matrices and you square them and add them all up. So that's the Frobenius squared distance. And I bring this up because the formula for chi-square divergence is extremely similar to it. So to define the chi-square divergence, it's almost the same formula. You go over all the entries and you take the difference of the two matrices and square it, but you multiply the ijth entry by a penalty factor, which is in general bigger than 1. And what is this penalty factor? The penalty factor for the ij entry of the matrices is this ratio, 2 over qi plus qj, where the q's are the diagonal entries of sigma. Okay, so let me just clarify the meaning of this a little bit. First of all, we're not going to be concerned about constant factors. So 2 is the same as 1 up to constant factors. And the sum of two things is the same as the maximum of two things up to a constant factor. So this is also sort of the same as 1 over the maximum of qi and qj. And then because I've ordered them, the maximum of qi and qj is always the one that's towards the top left. So in particular, it's q sub minim I and j. So let me just show you in a picture. You think of the matrices as being divided into these like capital gamma-shaped regions. And all the ones that have the same color get the same penalty factor. So in this first like blue top left region, you have this difference of the rho and sigma squared, and you multiply it by the penalty factor, which is like the reciprocal of q1. And then in the orange region, the penalty factor is like the reciprocal of q2. And in the green region, the penalty factor is like the reciprocal of q3, and so forth. And remember, these are like decreasing. They're numbers between 0 and 1. So these reciprocals are getting larger and larger and larger as you're going down and to the right. And in particular, since there's no inherent lower bound on the smallest eigenvalue can be like arbitrarily close to 0 or even 0. These penalty factors can get larger and larger and larger. So you're like getting penalized more and more the wronger you are about the sort of the bottom right parts of the matrix. Okay, so that's the definition of chi-squared divergence. And with that in hand, I can actually tell you how our tomography algorithm works to some extent. So a good thing about our result is that it's actually a black box reduction from tomography with respect to L2 squared closeness, or Frobenius closeness. So this is a problem that was not like inherently studied that much before, because Frobenius norm is not like the most natural way to measure the distance between two states. But in this paper from 2016, we showed the following result about full state tomography with Frobenius distance. You can do it with a Frobenius squared error epsilon using d over epsilon copies of the unknown state. And the proof of this is actually not so easy. It requires some representation theory. And actually, I really wish I knew a simpler one. And particularly now, because as I'll tell you, our results are derived in a black box way from this L2 squared or Frobenius tomography algorithm. I think it's like really motivated to try to get like a nice simple proof of this fact. I don't know one, but hopefully there is one. I'd also like to mention that this earlier paper from 2014 gave a result for tomography with respect to Frobenius squared error, which is really simple. It has an easy analysis, a natural algorithm, and it has the virtue that it measures the copies in an unentangled way. It measures all the n copies separately. The downside is it uses a factor d extra many copies. But if, for example, you want an algorithm that measures the copies independently, then this is a great and simple algorithm. Okay, so if we put that in our back pocket, we can actually get, as we'll see in black box way, tomography algorithms for other notions of distance. So in fact, this is how you can get tomography with respect to trace distance. So this works in a black box fashion. So the Cauchy-Schwarz inequality implies that like the square of the trace distance between two states, rho and sigma, is bounded by d times the Frobenius square distance. That's just matrix Cauchy-Schwarz. And therefore, if you get an algorithm that estimates rho up to error epsilon over d in L2 squared error, or Frobenius error, then that just gets multiplied by d and becomes epsilon trace distance squared error. And so just from the L2 squared algorithm that uses d over epsilon copies, this is how you get the d squared over epsilon copy algorithm for achieving small trace distance. Okay, so it just happens sort of automatically as a function of the L2 squared tomography algorithm. And in our work, we show that there's a black box reduction from L2 squared tomography or Frobenius tomography, even to all the way to like this ridiculous closeness of chi-squared tomography. And it's basically the similar form, like whatever the sample complexity is for L2 squared learning with error epsilon over d, that's basically your sample complexity for chi-squared tomography up to some multiplication by some polylog d and epsilon factors. And moreover, this reduction is very simple, and therefore it preserves any nice properties that your L2 squared estimator might have. So for example, well, I should say right away that, whoa, yeah. Okay, and the same way, this gives you that the chi-squared tomography algorithm with d times many more samples than you need for Frobenius tomography, and that's how we get our d squared over epsilon result for chi-squared. And similarly, you can get like a d cubed over epsilon algorithm for chi-squared tomography that is really simple and uses unentangled measurements by plugging in the KRT 2014 result I showed you on the previous slide. Okay, so in the last part of my talk, I just want to kind of sketch the reduction from Frobenius tomography to chi-squared tomography. And I can mostly give you the gist of how it works. The technical details are a little bit annoying. So there's an outer loop that you repeat logarithmically many times. And it goes like this. So the first thing you do is take your unknown rho, and you apply your Frobenius tomography algorithm to it with error parameter epsilon over d. And you get some estimate out, sigma, which is close to rho in L2 squared distance, and the closeness is epsilon over d. Okay, so you have this very good estimator in this weak notion of distance, L2 squared distance. And then sigma could be any old matrix, but because we really only know the formula for chi-squared divergence when sigma is diagonal, we just kind of in our minds, replace sigma with a conjugation by a unitary to make it diagonal, and whenever we access rho, we also apply that same unitary. So we can basically change bases in our mind to make our current estimate, sigma, diagonal. Okay, and so now here's the picture. We have this diagonal estimator for this unknown state rho. And we know that if this penalty factor weren't here, it would just be like the Frobenius squared distance, and that would be bounded by epsilon over d. But unfortunately, in the chi-squared version, you have this penalty factor. So the next step of the algorithm is just take a look at the diagonal entries in sigma and see like how big or small they are. And in particular, if like the first top left entry q1 is like pretty big, it's like 0.1, then this penalty factor, which is like the reciprocal of it, is like the reciprocal of 0.1, which is 10. And so a factor of 10 is not really a big deal to us because the L2 squared error is already very small. It's like epsilon over d. And in fact, even if you maybe consider all the q's that are at least as large as 1 over, let's say, 4d, then the reciprocal of that is upper bounded by 4d. And therefore, all these penalty factors are at most 4d, and like if you multiply that against the L2 squared error, which is epsilon over d, you get, okay, 4 epsilon, or order epsilon. So in other words, I mean, not worrying about constants, sort of the whole contribution to this chi-squared error coming from like the top left part of the matrices corresponding to going down to q that's as small as 1 over 4d are kind of okay for us. They're contributing error at most epsilon. So that's kind of good, and at this point you sort of you sort of freeze your estimate in this top left portion, and you say like this is perfect, and now I'm just going to try to work harder to estimate the bottom right corner of the matrix. And the good news is that you've made progress at this step because I mean if all the q's that you've sort of frozen are at least 1 over 4d, then presumably the rows are diagonal entries are also close to 1 over 4d. And in particular, there's at most d of them, so their sum is at most a quarter. So even if there's like a little error, the sum of the stuff that you've frozen is like at most a half. And sort of that means you've like bitten off at least a half of the trace of rho. And this remaining bottom right submatrix that you still have to estimate better has trace at most a half. Okay, and that's why there's like this outer loop that has logarithmically many steps. you just rerun the algorithm sort of restricted to this bottom right matrix, and that bites off another half of the trace, and you do that again and again, and it keeps biting off half of the trace. And then once the trace is like, really small, like polynomial in epsilon over d, you can do some trivial thing to finish it off. So this is the sketch of the whole algorithm. Just run L2 squared estimation, freeze the part where the diagonal entries are big enough, and then recurse on the lower right submatrix. Okay, so I'll just summarize what I've told you in the talk. So we showed that you can do quantum state tomography with sort of ridiculous closeness in your estimate. With the same number of samples, you'll need to, as was previously known, to just achieve like super closeness, so like infidelity at most epsilon. And we also showed a new testing algorithm, a quantum information tester, that given copies of an unknown state, a bipartite state, can tell the difference between the case where it's a product state versus there's at least epsilon mutual information and has linear scaling in 1 over epsilon. And in terms of open problems, a couple that come to mind are, first of all, I think this question of looking for a new L2 squared tomography algorithm is now a little bit more motivated. So I would love to see like a very simple algorithm for this if one could exist. And Steve and I really tried hard to get the analogous testing result for testing conditional mutual information. And it's trivial to make this extension in the classical case. But in the quantum case, like conditional mutual information is so hard. So we couldn't do it. But that's a good open question. OK, thank you.
Yeah, for questions, please come to the middle.
Hi, thanks very much for the talk. So this chi-squared divergence that you're using, I think it's the measured one, right? It's another way of looking at it.
That's right. It's the measured one.
So in particular, it's the smallest one that you could consider?
Correct. So it's the easiest one to do tomography with respect to. That's right.
Yeah. Do you have any idea for other?
Yeah, good question. So there's in fact like infinitely many natural generalizations of chi-square divergence to quantum state. Maybe a few finitely many of these are like particularly natural. And as was suggested, this one I talked about, this burst one, is actually the smallest one, so it's the easiest one. We did think about the like other natural ones, and it's our belief that you cannot get a tomography algorithm with respect to any of them except for this smallest one, but we weren't able to prove that with the same parameters, I mean. Okay. But that's a good question.
Thanks.
Thanks for a nice talk. Because I think you are talking about the chi-square divergence, and classically there's a symmetrized version of this distance called the triangular discrimination, right? So of course we can define also a quantum measured version. So I'm wondering, is that this kind of analog is also useful in quantum property testing?
Could be. Yeah, there are many, many more divergences besides the one I talked about.
Yeah,
I cannot remember like the classical, like the one you mentioned. It might be have the property that's the same as like Hellinger squared up to a constant factor. Or it might be the same as like one of these four that I mentioned are kind of in the classical world, kind of like the big four like well-known F divergences.
Yes.
And so a lot of the other ones often have the property that they're either bounded by these in both directions or even the same as them up to a constant factor. So there's so many of them, I can't always remember the precise relationships.
Yes.
So that particular one, I don't know off the top of my head.
Okay, so basically you're suggesting the starting point is like if there's some improvement about this inequalities, then it might be useful in some sense.
Yeah.
Okay, thank you.
Quick question. So for this first question, open question you have,
yeah.
What's the criterion for simple? Does it mean unentangled measurements? And do you predict that such an algorithm exists? Or do you think that this existing unentangled measurement algorithm is as good as you can?
Oh, yeah, good question. So it's known actually that, yeah, I'm pretty sure it's known that the unentangled ones require the more samples like d squared over epsilon. And if you want one that has the optimal dependence of d over epsilon, it has to be entangled measurements. So the criteria is simple, it's just to your taste, like maybe like a simple proof that like avoids a lot of representation theory. Yeah.
Okay, thanks.
So you said that your learning algorithm follows in a black box right from the L2 squared learning tomography algorithm, and also the trace distance one does. Do all of these tomography algorithms just follow from one in a black box way?
The proofs don't. But now, like I would say, like the one for infidelity didn't follow from L2 squared tomography in a black box where it didn't refer to it. But now I suppose retrospectively it does, because it's sort of essentially strictly dominated by the chi-squared one we talked about today. I mean, if you're not concerned about the polylog factors. Yeah.
This might be a silly question, but first, thank you for the talk. But when you mentioned there is a change of basis step in the algorithm, does that involve like actually applying any unitaries, or is that like implicit?
No, I guess you would have to apply unitaries. Like you have to take your copies of rho and like you figure out on a piece of paper what are the unitary you would like to apply to it, and then every time you like act upon rho, you have to also apply u to it.
Yeah, but like does that rely on any other information, like because you want to change sigma to like a diagonal matrix, right?
Sorry, I didn't understand the question.
Does that rely on any information, like so?
So the unitary comes from sigma. So like given rho, first you make your first initial estimate sigma.
Okay.
And then you like diagonalize it by yourself by hand and find the unitary
Oh,
on a piece of paper that does the diagonalization. And then like you use that unitary to like rotate rho for your subsequent refinements.
I see. Thank you very much.
Yeah.
Okay, let's thank the speaker again.
Thank you.